Start with the next talk. Now I have to find the name, sorry. Daniel Schoepe will talk about on-demand analysis, and you can start.
Great, thanks for the intro. Thanks everyone for coming to my talk. My name's Daniel. Oh yeah, there's the slides. So I'm going to be talking about on-demand call graph construction. This is work that David Seekatz worked on during his internship at Prime Video, and also the rest of my colleagues in the same team contributed as well. So let's motivate a problem. So it starts from the observation there's a lot of interesting static analysis problems require us to reason interprocedurally. So as a motivating example, let's look at the problem of SQL injection. So let's look at this program here where we're creating a SQL query here based on some input. And let's ignore for the moment that you shouldn't be concatenating strings to create SQL queries, but for the sake of this example, please bear with me. So if we want to reason about this problem, we want to figure out whether the name variable there may be user-controlled untrusted input. So in other words, this is a taint tracking problem where this prompt function here can be considered as a taint source, and the connection.query function there can be considered a taint sink. Now, in order to figure out what actually flows into this taint sink, we need to reason about where this anonymous function that's being returned from getQuery actually is invoked. So that's pretty, in other words, we need to construct a call graph. There are some easy cases where you just call a function by its name, like calling getQuery at the end of the program here. But in many modern languages, you have higher order features as well. So the function getQuery actually returns another function that gets bound to a variable and then called. And then these call edges that involve higher order functions are a bit trickier to detect. But that's still pretty straightforward if you just have a bunch of code that still fits on one slide. More realistically, though, these two places in the code might actually be very far removed. There might even be millions of lines of code in between. And then at that point, it becomes pretty hard to actually build a call graph for the whole program, because you need to reason about all the stuff that happens in between there as well. And now at this point, you basically, the most standard approaches, they build a whole program call graph where you are faced with a trade-off. Either you can try to be precise and not get too many spurious call edges, but then that can be pretty slow depending on the exact abstractions that you're using. Or you can use a faster approach that then is more imprecise and may create a lot of spurious edges in the middle there that aren't really corresponding to real program executions. So that trade-off is a bit unfortunate, and ideally what we would want to do is to really only care about these relevant edges that somehow involve either taint sinks or taint sources or both, and not about all this irrelevant code in the middle that isn't relevant for a particular goal that we're trying to prove. So what we really want to do is reason just about the necessary call edges in a demand-driven way, rather than having to analyze always the entire program. So that sounds like a pretty simple and straightforward idea, but it's actually not so easy to do that in practice. And the main reason for that is that if you have higher order functions, you're essentially connecting your data flow with your control flow. Depending on what you do with the function that you use as a value, if you store it on the heap, you retrieve it again from the heap somewhere else, you now need to reason about kind of your data flow and your control flow at the same time in sort of a mutually recursive way. And in particular, also, this work is motivated by the fact that a lot of the state-of-the-art work, including on-demand analyses, still assume an upfront whole program call graph. So for example, there was this very nice work at PLDI 2 years ago that took an arbitrary abstract domain and showed how to turn it into an incremental analysis, except that you still needed this upfront call graph. So what we're trying to do here is help close this gap and allow us to build sort of a fully on-demand analysis that can then hopefully scale better to large programs. So to summarize the contributions I'm going to talk about, we start from the scenario where we have some client analysis and we have our on-demand call graph algorithm. The client analysis will then ask some questions to our algorithm, like what are the callers of function f, what are the callees on line 7, things like that. And our analysis is parametric on an underlying points to analysis that we then use to answer these queries. And the points to analysis that we rely on can itself assume a call graph, and I'm going to show how we can essentially bootstrap a call graph from nothing in order to answer these queries, and then get back to client analysis with some answers. Then we, on the theory side, we formalized an abstract version of our algorithm, and we defined what it means to be on-demand sound in the context of call graphs, and then taking that together, we proved that our approach actually is sound, and we verified that with Isabelle. On the practical side, we implemented the approach for a small subset of JavaScript using synchronized push-down systems as an example of like a modern points to analysis framework. And we evaluated that approach against essentially running the same approach on the entire program versus just on small subsets, on just individual call sites or functions. So to show you how the approach works at a high level, let's consider again sort of a modified version of the initial example, where, and let's say that we want to figure out what are the possible call targets on line 11 there. And we're going to do this by interleaving two types of queries. We are going to ask some underlying points to analysis, what are the values some expression E can have on a particular line, in particular what function values can it have. And also we're going to sometimes ask what are the callers of a given function across the whole program, some given function f. So when we want to figure out what are the possible callees on line 11, for example, we would start by issuing a backwards query asking what value can the variable f here have on line 11. And then the first thing that the analysis will do is realize that, oh, so okay, we go backwards from there, and then we reach the beginning of this run and say hello function. At that point, we realize f is a parameter, so really to figure out what value it might actually have, we need to figure out where run and say hello is being called. So we would issue a forwards query saying, where is this function being invoked? In this case, it's very straightforward. We just see direct static syntactic reference to it, and we can figure that out just like through lexically looking at the program. And then we add, but in principle, this could also be more complicated, like run and say hello might itself be used in a higher order way and being passed around and so on. So then we add an edge to a call graph saying, okay, line 17, there's a call to line 10 that's relevant for answering our initial query on line 11. At that point, the initial query trying to resolve f can make progress because now we know where run and say hello is being invoked. So in particular, we now see that this query argument passed to the call on line 17 is going to be going to determine the value of f. So then we keep going backwards on that query, trying to figure out what does the variable query contain. So then we see that it's being returned by this getQuery function, and in principle, that could also be a higher order call. So first we have to also resolve what is getQuery actually calling. In this case, it's again a simple statically resolvable call. So we add another edge for that, and then finally we then get to the actual getQuery function body, and here we see that we return a value from there that then flows into query, and then that flows into f. So at that point we're essentially done and can add the call edge that we actually care about to the call graph. So the call on line 11 to the function, to the anonymous function returned on line 2. And in principle, if there were other references to run and say hello in the rest of the program, we would have to keep going until we find all the possible arguments that are being passed to that. But in this case, this is the only reference there. So we're done and can say, okay, that's the relevant bit of the call graph that we needed to construct in order to answer the call targets on line 11. And I want to emphasize here again that so we're parametric in how we answer these blue and orange arrow queries there. Under some assumptions that I'll get to later. All right, so that's the basic overview of the approach. Now the question that some of you might have, and that we certainly had when we came up with this, since we're sort of using all these queries that need information from each other, can it be the case that there are cycles between queries? So could we have, for example, some cycle of 3 queries that we need to answer in order to make progress on each one of them? So the question is, when does this happen? Can this happen? To which the answer is yes, this definitely can happen. So here's a fairly minimal example. So let's say that in this example, we want to now find the callers of function f. And then we could start from individual syntactic references to f in the program and see where they flow and where they might be invoked. So for example, we could start in the body of G because f is being referenced there, like statically. So at that point, we see that we get to the end of function G, and we need to figure out whether this E parameter is eventually going to call its argument or not. So we need to ask what is this E value actually? What is this E variable actually going to contain? At that point, we reach the beginning of function G and say, okay, then in order to figure that out, we need to ask what are the actual call sites of G? So again, we would start from where G is being referenced and see where then that might flow. So we would start here. At that point, we would have to, we would again reach the end of function f, and at that point, we would have to again figure out what are the actual callers of f. So we're exactly in this cycle where we would sort of first get an answer to a previous query to make progress on a later one. So what can we do with that? So the key intuition to solving that problem is that if we look at an actual execution trace, then the things don't happen in this sort of cyclical way. They happen in order of the actual data flow in the program. So for example, you would first pass G to F, and then that in turn would enable calling G from line 3. That would in turn enable calling G from line 6, and that would in turn enable calling F from line 6, for example. So there's always some previous data flow starting from some reference to a function that then gets passed around and then gets invoked before a call actually happens. And the key thing that I want to emphasize here is that these, like in a real execution, calls to different functions and these data flows of function values are interleaved. So, and we were before trying to sort of answer one query at a time. So that's kind of a mismatch. And the intuition to our solution here is, well, since the function calls are interleaved and there's all this sort of like interleaved stuff going on, why don't we interleave the queries as well? Which is to say, like, let's try to answer them concurrently. So saying, if we have like query 1 and query 2, then we run query 1 for a bit. Whenever that makes progress, we can inform query 2 that we found another call edge that's related to query 2, allowing that to make a bit more progress. That in turn may enable progress of query 1 again, and so on, until the whole thing reaches a fixed point. So that's the overall intuition. That still seems a little bit ad hoc, and like, does that really work? I don't know, seems a bit dodgy, doesn't it? So in order to make sure that we didn't miss anything there, we wanted to prove a soundness theorem about relevant bits of the real call graph. And I say relevant bits here because we need to recall that we're doing an on-demand analysis. We don't want to have to over-approximate the entire call graph. We just care about a little bit of it. And our soundness, and the way that we formalize what the real call graph is in order to not tie our approach to particular languages, a particular syntax, particular heap memory models, heaps, and so on. We just model the program as some function, the semantics of the program as a set of traces, where the events in the traces are things that are related to calls. So you can see that as essentially collecting semantics that only cares about what function calls happen and what references to functions are being passed around and things like that, without fixing the exact memory model on language features around heap and so on. So now the soundness theorem that we are then proving about this real call graph is the following. So if our call graph construction reached a fixed point, where this squiggly arrow here is essentially a non-deterministic sort of transition system that can perform one of the steps we've seen before. So we can add an edge to a call graph based on data flow that the points to analysis already found, or we can start new queries based on what we still need to answer. When there's no more step that can happen here, then we want a certain soundness statement to hold. And typically the way that you would end up in this situation is that you start from an empty call graph and some initial set of forward queries, fs0. So essentially you want to find out what are the callers of these particular functions, and a set of backwards queries, es0. So what are the values some particular call expressions can have at runtime. Those initial sets might come from the client analysis that wants to answer something like a taint analysis problem or something like that. Then you run the algorithm. You perform a bunch of these steps, possibly in sort of a non-deterministic order. You can run them concurrently. You can also run them in parallel. Then, as that happens, the set of queries, you might issue some extra queries in order to answer the original one. And then, after that process terminates, the call graph CG that you get out at the end that is going to over-approximate this intersection in the middle here. And this intersection in the middle is exactly the part of the call graph that we care about. Those are essentially all the calls that involve either a function for which we asked, where is this function being called, or it involves a call site for which we asked, what are the callees of this particular call site. So that's essentially the theorem that we've proved under the assumption that these points to analyses that answer individual queries are actually sound. And I'm going to tell you what that means on the next slide. And yeah, since this involves a lot of like tricky reasoning about sort of getting the fixed point correct, we formalized that in Isabelle to make sure we didn't miss any corner cases. All right. Now let's talk a bit about these soundness assumptions on the underlying points to analysis. So the format, the interface that we expect from these, I'm going to go over the forwards example. The backwards one is kind of analogous. is the following. So we assume that these points to analyses might need a call graph up front to make some progress, but this can be a partial call graph. And then you also give it a query. For example, you ask it, where's f being called? And then what we require of this analysis in order to consider it sound in terms of the assumption of the previous theorem is the following. When there's a real trace in a real execution of the program, where we give it a partial call graph that's compatible with some prefix of this trace segment relating to f, and then there is a real trace that ends up calling f from some other line as the next event in the trace. And what happens so far in the trace is compatible with the call graph that we gave to the forward points to analysis, then it must be able to discover this next event in its abstraction. However, it's representing trace sets, so you're typically going to have some finite abstract domain that would actually represent the actual sort of sets of traces here. So intuitively, that means that if you ask one of these on-demand points to analyses a question and you have some data flow from some reference to function f somewhere, and it passes it around, but the trace so far only involves call edges that you have already discovered, then you are expecting this points analysis to correctly track the data flow across these call edges that you already told it about via this partial call graph. So that's essentially the soundness criterion for the forward points analysis. There's a similar backwards one. And we think a nice part of this approach is that in using this modeling, we didn't at all have to think about what kind of data flows are there in the program, like what's the heap, where can you store functions, how can you pass them around. So that simplifies quite drastically the amount of sort of formal modeling we would have to do of the language in question. It's fairly general. All right. Let me quickly then go over the rest. And there's also some additional assumptions around reflection. Let me, before wrapping up, talk a little bit about the evaluation of this. So we implemented this for a pretty small subset of JavaScript, instantiating this SPDS framework, Synchronized Push-Down Systems, for that subset. We didn't do it for the whole language because it's a fairly complex framework, and handling modern JavaScript introduces all kinds of like pathologies you would have to deal with. So we focused really on sort of the higher order aspects of this. We then generated a synthetic data set that artificially creates a lot of like higher order function calls where you return functions, you pass them around, and so on. We use QuickCheck for that to have a nice way to sort of generate structured random data. And in the future, we leave extending this to like handle modern JavaScript code up to future work. The implementation is online. You can find the artifact link in the paper. It also contains the Isabelle theories if you want to take a look at the soundness statement and so on. Now let's talk about the results here. So we essentially wanted to answer, does this approach actually allow us to not have to think about the whole program, or do we end up in this kind of degenerate case where we need to still answer every query about every single call set in the program to answer some initial one? In order to figure that out, we started with a bunch of essentially sets of initial queries. The x-axis here essentially represents selecting n random call sites in the program and asking our approach to resolve it. And then on the y-axis, we see how many other queries did that require resolving. And we do see that this does indeed increase as we sort of ask for more call sites to be resolved initially. In terms of runtime, we first got a little bit of a surprising result here. So the black dots here are essentially our baseline where we upfront ask it to resolve everything in the program to kind of model a whole program call graph approach. And then the first surprising thing is that yes, on the left part of the graph here, we are sort of faster than computing these black dots, but for larger query sets, that is not always the case. So we were scratching our heads a bit and like, wait, why is that happening? But then we remember that this approach really relies on concurrency in order to be correct. So we also implemented it to use parallelism, multiple threads, and all that. So we were suspecting that might be the culprit. And indeed, when we then actually measured CPU time as well, we got a more expected result where answering more queries will actually take more CPU time. But if you ask for all of them up front, you get a lot more opportunities for speed up from parallelism. Otherwise, you might start answering one query, the other cores are sitting there doing nothing, you get a few more queries later on, then two more cores can maybe do something, and then you end up wasting a bunch of like wall clock time compared to if you just ask it about every call site from the start, then you always have enough analysis to do essentially. So that's the performance story there. So if you care about energy consumption or stuff like, yeah, for some reason CPU time is more important to you than wall clock time, this might still make sense. For instance, like in an interactive setting in IDE, you might not want to really use all the cores of your system constantly to answer this quicker. So summing up, I showed you an on-demand call graph construction approach that's parametric in an underlying points to analysis. So we can use existing state-of-the-art points to analyses like SPDS that assume a call graph, but we can then bootstrap a call graph kind of out of nothing without having to do any kind of upfront whole program analysis in the first place. We formalized it and proved it sound, and you can take a look at the artifacts online. That's it. Thanks for listening.
Well, I have a question. You use as a baseline your own tool running on all possible queries. Why didn't you consider choosing a all program construction tool?
Yeah, that's a good question. We debated whether or not we should do that. But essentially, at that point, we would be essentially comparing SPDS to like a different algorithm because there's no like whole program SPDS instantiation for JavaScript. So we wanted to really compare like the same points to analysis on demand versus the same points to analysis whole program. Otherwise, we might be measuring all kinds of things that are not really super relevant to whether this on-demand approach gives you any savings.
Okay, so there would have been too much noise. That's the reason. Okay.
Yeah.
Are questions?
Thank you. Thanks for a very nice talk. So I was wondering if you're running the on-demand analysis, you couldn't use the concurrency as much. So could you do something to evaluate some parts on speculation? Maybe you can use ML for that. I don't know.
Oh yeah, that's a good point. Yeah, I think that would work. You could always just run a bunch of queries speculatively in the background, and then if later on they turn out to be needed, and the first query will sort of ask the system whether the query has already been answered or whether it should start it, it will already get the answers. So yeah, you risk doing a bit of extra like unnecessary work, but you would get the same kind of speed up as for a whole program setting, I guess.
Okay, other questions? So no, so let's thank again the speaker.